Recording. Okay, so today we're going to talk about chapters 3 and 4. So these are groups and properties of groups. And I think we're going to fly over the actual chapter and we're going to probably go to some of the quote unquote interesting exercises. I'm starting to consider re-adding my tablet for drawing in the computer because we will reach a point where drawing will be mandatory. And I think that these two chapters gave me the okay, maybe I should open the closet there and pick my tablet and connect it back to the computer. So I'm considering doing that, but I don't have that setup done today. So, groups. What is a group? In a very mathy fashion of cumulative definitions, a group is defined to be a set with an operation which is associative, has a neutral element, and each element has an inverse. Um, these can be written in this notation. And now we have examples, right? So, for example, this integer set, and we have addition, which addition combined with this set forms a group because addition is associative. There is a neutral element in respect to the set and the operation itself. And in regards to the operation, each element has an inverse. So then there's a bunch of examples of rationals and stuff. Um, and then we go actually to a very interesting application, which is the groups of integers modulo n, which, well, as programmers, we are very familiar with this operation, right? But I never
Yep.
actually thought of like a pictorial representation of this process, and then this is one of them. That's nice.
Oh, wait, you've never seen a clock, Lemus?
That's
An
not what I
analog
said.
clock?
That's not what I said. What I said is that I never thought of a pictorial representation of this procedure before. Of course, I've seen a clock, but I never seen the clock in the context of being a way to represent this operation.
That's weird.
Yeah, I always interpreted modulo as just like a complementary operation of division. I never thought of a clock to represent that.
Yeah, no, modulo is kind of its own thing. It's a big deal, actually.
Yeah, yeah. Anyway, so you can use this, and the reason this is useful is because using a clock you can naturally fit the whole overflowing thing that you have to restart. And it is a very useful operation for many reasons. You can generalize the clock by using well 2 pi divided by n and things like that. Um, it has an inverse, it has a neutral element. So this is a group with integers. Often when working with finite groups, it is useful to draw up the operation table. So this is essentially a table that maps the operation with the operands. So with these two operands applying this operation, we have this outcome. And very basic. And then this is how it works. So each row for each element of the group and one column for each element of the group. Then 3 plus 4, for example, is located in the row 3 and the column 4. So it looks like this. The entry in the row x of the row of x in the column of y is x operation y. Let us remember that the commutative law is not one of the axioms of group theory. Hence, this identity is not true for every group. We've seen this with matrices before. But if that happens to be true, then the group receives a specialization, a Abelian group. And it is named after this guy that probably we saw in chapter 1, but I forgot all the names already. And that guy was a pioneer in the study of groups. And then if you have these 6 matrices with the operation matrix multiplication that was explained before, this group, speaking of page 4, I have the book.
Oh, that's nice.
4 or 8, right? yeah, this group has the following operation table, which should be checked. So very fine. In linear algebra, it is shown that the multiplication of matrices is associative. Uh, well, we already know this because this is a group, so it is associative. It
Yep.
is clear. Yes, Mari.
Yeah, we've seen this, and in fact, I think it would be more appropriate to say that this is a group because it's associative, not the other way around. But then, why would it be used then as an example if it's not actually a group, right?
Yeah, yeah. I don't think the book is saying the other way around, but it's trying to put another justification. Instead of saying that the multiplication of matrices, um, well, I guess that's this is fine. It's because the order of the cause and effect matters, right? So it is a group because it is associative, but it is associative being proved by linear algebra. So that's the causality chain. It's not the other way around. It is not associative because it is a group, right?
Yeah.
It is clear that the identity matrix is the identity element of this group, and by looking at the table, one can see that each of the 6 matrices has an inverse, which also just happens to also be contained in the group of 6, each inverse. Thus G is a group. Now we can observe that AB equals C and BA equals K, so it is not an abelian group because it's not commutative. And now becomes the exercises, which do you guys have any remarkable points to make?
Uh, there is one that I noticed actually on, I think it's on the section B. Um, yeah, point 4. That's actually the complex numbers.
Okay, so if you have pairs, yeah, so okay, this is also explaining how you do things with pairs. Because you have to also check for the inverse and the identity. So this is how you check for the identity, and this is how you check for the inverse. And the operation that we're doing is essentially saying that the operation on this pair becomes this operation. And Maria is
Yeah,
saying that
and
this is
that
the complex
actually,
numbers.
yeah, that actually defines the complex numbers.
Mm, it is true. Okay, I think I should explain this because it's not in the bucket of what I consider to be trivial. So why is that? It's because when using pair notation for complex numbers, you have to remember that the second member is always the complex portion, imaginary portion. So this means that this a here is a normal number, and the b will be multiplied by I, and the same applies for d and c. So if you do the distributed property of multiplication, well, not because this symbol is usually used for multiplication, but assuming it is, just for the sake of demonstration, it's going to be what? A times C, A times D, B times C, and B times D. However, when B is multiplying the D, because both of them are imaginary portions, that's going to become a minus, because I squared is equal to minus 1, so this is how this minus comes in. And everything else is everything else should be just follows, right? So yeah, this is how you can encode complex numbers.
Oh, multiplication on complex numbers in specific.
Yeah, multiplication on complex numbers. Assuming it's because this symbol is kind of misleading. This doesn't need to be multiplication, but in
But
this
in this
case, it kind
context,
of
it is.
fits.
Yeah. Yeah, in
Uh,
this case, it actually is.
yeah, so just for like just to clarification, it's just a coincidence that this symbol is usually denoting multiplication. Anyway, so about the exercises, I think the one that I would like to highlight is C because well, all of this is kind of fine, but then well, I kind of felt this portion of the exercise kind of random. We kind of started with a particular context of defining what symmetric difference is, and then out of nothing, this. But I guess this is fine, and I think the identity element of this thing is like empty set, isn't it?
It should be.
Which of course has an inverse, and we can use this other PD thing to prove it. This is also pretty cool. This whole like moving things vertically, horizontally, and diagonally, and there's some invariance that you have to hold. Same thing with the coin, that you can do a bunch of moves, and they hold invariance among them. That's cool. And you're gonna figure that out by writing this table, and then you're gonna be able. Essentially, these exercises are enumerative in the sense that you can enumerate the possible combinations using the table. So you're gonna be pretty clear the answers to these questions, right? So it's not that big of a deal. And then some programming shit. And then some programming shit because it's essentially explaining how to do addition with binary.
Oh, actually,
Uh,
it's XOR, not addition, but yeah.
XOR. Well, but addition removing the carry
Y-
is XOR. So
Yeah, they're using the symbol for addition, but it's actually um, bitwise XOR.
yeah, no. But if you consider the carry, the because this is a one bit a portion of the addition, right? But you
Yeah,
are
but then
ignoring the carry.
yeah, it's extending the to the multi-digit case by ignoring the carry. So yeah, it's not actually addition, even though they are using plus.
Uh, they are ignoring the carry. Yeah. Yeah, and then that is yeah. This one doesn't hold. This is on addition, right? Because this one times one plus one with the carry on another one plus one should be one, and it's zero here. So this is just XOR. Yeah, you're right. Anyway, so then it starts like, oh, actually, these sequences of binary, it is commutative in a, well, this operation on these sequences of zeros and ones is commutative, associative. There is an identity element and there is an inverse. Um, this is just associativity, finding the identity and inverse, and being an XOR, doing the XOR with the one's complement, right? This is one's complement.
Uh, a plus b equals a minus b, where
Oh, they changed this. In my book version, I don't have this asterisk here.
yeah, I think that asterisk is not supposed to be there.
Yeah, but I think this is essentially like one's complement, right? This thing, because you're gonna negate the thing. Negating the thing is flipping the bits, and
Yeah,
flipping the
bitwise
bits without
not.
doing a plus one is one's complement.
Yeah, it's bitwise not, which is equivalent to one's complement if you consider integer arithmetic, right?
And if you do an XOR with one's complement, is the output different? What do you say?
Well, if you negate a word and you do an XOR, you should get a zero no matter what
No,
at
no,
the
no,
end.
no, 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 no. But that's not what we're doing. We're doing the negation on the second operand because we're trying to prove that doing XOR is the same as doing XOR with the one's complement of the second. This is what we're trying to prove, right? Assuming that the doing the negation is one's complement. But now that I think about it, I don't think it is, right? Because if you negate the B in here, if you take a look on here, if you take this second operand here and you do one's complement, which is flipping the bits, and you shore the first with the inverse of the second, that is not getting you the same outcome, right?
Yeah, that is weird.
Yeah, so either I'm interpreting this wrong and this negation is not actually one's complement. Dev, what do you think?
Is XOR not its own inverse? And thus negation is just XOR. I mean, that's what the exercise is telling you to prove, but
Wait,
Oh, right, because this is not necessarily like this minus is not necessarily integer negation or yeah.
that's the inverse operation.
Well,
In
yes,
theory,
the
for
XOR is
XOR
its
is
own
XOR.
inverse. Yeah, XOR is its own inverse. So yeah, a plus b must be equal to a minus b because plus and minus are the same thing in this particular group.
but why does the example doesn't follow then?
What do you mean the
What?
example doesn't follow?
Exactly that. If you pick the example and you apply this definition of subtraction to the operands with the first binary number being a and the second binary number being b, my understanding is that if I do that and I do the negation on b and do plus with a, I should have the same outcome as the original one.
Mm,
And I don't know if I understand what you guys mean by XOR is its own inverse. Inversion is not made on top of operations, but on the element. So, what's up with that?
mm,
Hmm. Marinho? Am I not making sense? Hello? Did I drop?
I'm no, you didn't.
In theory, negation is identity because
Wait, what?
well, if you XOR a word with itself, then you're going to get all zeros, which is the zero um of the group we are talking about.
So yeah, every element is its own inverse, basically.
Yes.
Ah, okay. It's because no, what you said is exactly what I was missing. The inverse of something in the respect to XOR is itself, which means that you do not flip this, which means that the outcome is the same, and then a plus b is equal to a minus b.
Yes, because minus b is well, identity
Yeah,
essentially.
no, that was my mistake. The negation in this case to make the inverse is actually itself, not flipping the bits. Cool. And then some coding stuff. Like this is which layer? Transport layer? No, not transport, but there was the whole stack thing of software. This reminded me of that we have like parity bits and we have like things like that and redundant bits, redundancy positions. I studied that in college back in the day.
Yeah, this is basically about how you can encode information in binary form in such a way that if you get some errors, maybe during transmission or maybe some cosmic rays hit your hard drive, you can detect those errors and correct them. That
Yeah.
implies that you must not use all of the bits to store information. You must use some of them to, well, to store some redundancies so that in case you get a flipped bit, you can see that, oh, yeah, this with this redundant data actually doesn't match, so we
Yeah.
can do something about it.
And there's also the ambiguity thing because this is this minimum distance concept is because you may have ambiguous decoding, given that you may be able to detect errors, but depending on the positions where those errors are happening, you may have two different like correct code words, and then you need to use the minimum distance concept to make sure that a lot of bits needs to be fucked in order for you to have ambiguity. So that's great. And then I think that the thing that I would like to talk about is number 6. Right. So um, uh, well, number 5 is kind of, in my opinion, kind of. if my understanding is correct, this is kind of like a consequence, because if the m is the minimum distance, everything below m it's fine. That's kind of the point of having the minimum distance. That up
Yep.
to it you don't have ambiguity. After m you are completely like no luck, out of luck. But 6 is kind of interesting because of this formula here. So it's m minus 1 divided by 2. So by the sphere of radius k about the code word a, we mean the set of all words in B and N whose distance from A is no greater than k, right? So it's essentially saying that SA is all the pairs between the code word A and another sequence of bits in which the distance between those two is less than or equal to k. So all of these pairs, we're putting them in a named set called SKA. But if we make a T in which is using M, which is the minimum distance, we have to prove that any two spheres of radius T, say those two, have no elements in common. So I don't know if oh, there is a hint. Assume there is a word X such that X is contained in both, using the definitions of T and M, show that this is impossible. So how would you go about to prove this one?
Uh, well, the radius is just half of the minimum distance. It's actually slightly less because
This is
there's that
slightly less.
minus one there,
Yeah,
right?
sure.
That means that for something to be in both spheres, the two spheres would have to overlap. But because the radius is actually less than half of the minimum distance, they cannot overlap.
When you say overlap, you say that the ambiguity could lead to either of them.
Yeah, overlap means you have an element that actually is in both spheres, right? Which is what they're trying. Basically, the point is, since the radius, in order for the overlap to even be possible, the radius of each sphere needs to be at least half of m, right? That minus one over there is kind of making sure that there will be a gap.
Yes. Okay, so when you say
Oh,
overlap, you mean that you have an element that can be in both spheres at the same time.
yeah.
But that's um
I'm basically just borrowing intuition from geometry here, to be honest.
no, yeah, but when you say that and when we have that the distance is a little bit slightly less than half of the minimum distance, this means that uh what does this mean? That's a part that I have a hard time figuring out without paper. I understand what you said, but I don't. I'm not able to progress to go to the conclusion that they cannot have elements in common.
Okay, basically, the minimum distance between, like, the minimum distance in the set of elements is basically the smallest distance between any two elements, right?
Yeah.
So if I make a sphere around each element, and the radius is exactly half of the minimum distance, then every sphere will be tangential to its neighbors, right?
Every sphere, yes.
So if the radius is less than half, which it is in this case, then the spheres will not touch at all, right?
Oh, so if
There
the,
will be a gap.
if there's no overlap, no elements can be in common.
Yeah.
I see. I see. Okay. Yeah. No. Okay. Deduce from part 6 that if there are t or fewer errors of transmission in a code word, the received word will be encoded correctly. This is again, you don't need to use part 6 to deduce this, because if t is equal to this, by definition of when m is, this is already tautological, right? Because if t was equal to m, this would still be true. But if it's half of it, then it's guaranteed to also be true, right?
No, because if t is equal to m, then actually that's sufficient to cover the distance between any two elements, right?
That's sufficient to cover the distance between any two elements. Two elements of what? The code word, right?
The code word, yes.
No, but the minimum distance concept says, my understanding is that if you are at maximum m, you are good to go. Aren't you?
No, the minimum distance is how far you have to go um, to bridge the gap between the two elements that are closest to each other.
Oh, but that's a consequence. What you said is also right, but that doesn't imply what I said is wrong.
No, but for then it follows that, okay, if you have a number of errors which is t, which is less than half of that, then that means it's inside of the sphere of that radius that's around each point, and we know those spheres don't overlap, so...
No, but I'm trying to make a second point. Imagine that it was not half of m. Imagine that t was equal to m. The spheres
Well,
would be immediately the spheres would be
that doesn't help because then every sphere would have at least two valid elements.
it's because I'm making confusion between diameter and radius, right? So if you are
Actually,
at m distance, that is covering the centers of like the two cold word centers. That's the difference between them. If you make a
actually,
sphere,
yeah,
yeah,
actually, it's not even every sphere. It's just there is one, at least one, where there are two elements, and if you find that in that space, then you don't really know which element you should go into.
yeah, it's because in that case, in geometric terms, man, we should have the drawing. In that case, in geometric terms, there is a sphere doing this with the other one like this, and it's touching the centers of each one, right?
Yeah, if you're exactly between those two
Yeah,
spheres,
t equals
or
m
rather,
in
if
this
you're
case.
exactly, yeah,
Imagine that
if you're
t equals.
exactly, yeah, if you're exactly at t equals m, you can move from one valued element to another.
Yeah,
If you're at t equals half of m, and you happen to be right between those two that are m apart, then that's ambiguous. So yeah.
yeah. So that's actually a little bit confusing because uh, is at least. Okay, it's because what I understood of minimum distance is not correct. The minimum distance means that at least that distance errors of transmissions are needed in order to transform a code word into another code word. That's kind of funny because if it is the minimum distance or less,
It needs to be less than half of the minimum distance for you to be able to correct the error, basically.
but what is written here is that if you have the minimum distance, like from the minimum distance above, then the code word transformation happens, right?
Yeah.
But what you said is that you need it to happen only half of it to correct it.
No, no, no. If you go, if you,
That's kind of
if
funny.
the, like, if the distance between the corrupt code and a valid code is less than half, strictly less than half of the minimum distance, then because because of that argument about okay, the spheres don't overlap if they have that radius,
Yeah,
then yeah, you can just go to the center
yeah,
basically.
yeah. You can go to the near center of sphere, which is going to be that one. But what this is saying to me is kind of different. This is saying that after the minimum distance, you can have transformations of the code word into another code word, right? You don't know which
Well,
center to
yes.
pick.
Well, yes. Actually, this means if the number of errors is equal to the minimum distance, then it's possible for a valid code word to become another valid code word by
Yeah,
definition.
yeah, but there is a gap there. You see, because imagine that m is
Mm,
here. M is m divided by two. M minus one divided by two is here. So we know that from here onwards you are screwed, and we know that from here there you are good. What happens in this middle?
In that middle, you can detect that there was an error, but you cannot fix it.
Ah, okay. So there is a okay. So this is what I'm getting this wrong. You can detect it, but you cannot do anything about it.
Yeah.
I see. Cool. Okay, so I take that back. I just misunderstood this. So this is actually like a good exercise. What else about chapter 3? Does anybody have anything else, Tevo? Any comments about the exercises in chapter 3 that you want to highlight?
Not really, no.
Okay, cool. So 4. Properties of groups. Elementary properties, right? So is it possible for a group to have two different identity elements? Very good question. So imagine, assuming that there is, but because they are both identity elements, this is true, and this is also be true, but then they must be equal. So no, there can only be exactly one. And the same thing applies. Okay, that you have to do some massaging with associativity, but the conclusion is always also the same, exactly one inverse. Then he talks about notation. That I think this is a little bit repeating itself, but okay. Um, uh, yeah, and then we have the because of the additive notation and multiplicative notation, you can have the inverse written in different ways, which is also fine. And then we actually go to and this is the beginning of something very important. The most basic rule of calculation in groups is the cancellation law, which allows us to cancel the factor a in the equations ab equals ac and ab equals to ca.
Yeah,
Uh,
that's a misprint. It actually should be BA equals
yeah,
CA.
yeah. Actually, there is a question in the new version here. Wait, wait, what? Oh,
What
here.
do you mean?
No, this is what makes it a misprint, right?
I figured
Yeah,
that is what the bad Amazon reviews were about. The ones that were complaining about the
Mis
Kindle version.
No, no, no. But yeah, no. But I think. Wait, let me check the if there's
Like
a.
I have the physical book here, and the physical book has that written correctly.
Oh, okay. So that is true. Let me check. It is written correctly.
yeah, the
No, it
theorem is
isn't.
right. It's
No, it
just the
isn't.
body of the. It isn't.
I don't know about Tevo's
Oh
version.
no, it is
My
not.
version, it is
So
wrong.
I'm looking at the wrong place. Yeah, it's wrong. You cannot.
It is at least consistently wrong. Okay, we're gonna explain why this is wrong because we all three understand, but we are recording this, so let's say why. So the theorem one goes as follows. So AB equals AC implies BC, and BA equals CA, which is what was supposed to be written here, implies B equals C as well. And why is that? Well, suppose this, right? So AB equals AC. Then, if you multiply on both sides on the left, and the side kind of matters here, by the inverse, and then we apply associativity, we get this multiplication, which by the definition of groups, we can put this to rest as the identity element, which applying again definition of groups, this identity element when apply the operation to any other element, it becomes only itself, so B is equal to C. And the same can be done in analogous with this one. But
With the
then
element on the right, yeah.
why we cannot cancel this? Because this imply to make this true, you have to also be an abelian group, which we are not.
Yeah, it requires commutativity, which is not true in general of groups.
Exactly. So this is true for abelian groups, but not for general groups. Yeah, I actually didn't notice this before because to me, I kind of like, especially when I read this, I was like, yeah, no, this makes complete sense. But anyway, so theorem two. So this one is about inverse in identity. So if G is a group and A, B are elements of G, then if we know this implies that A is either B the inverse of B or B is or the B is the inverse of A.
Actually implies both things. It's an end there.
Implies both things. Yeah, sure. The proof is very simple. If A, B equals E, then if you multiply well, if you undo the identity, you can say that it's equal to A operation with A's inverse. And so by cancellation that we just used by theorem 1, you can cancel the A on both sides, and then you have this, and you can do the same by saying that E is equal to B and B inversed. This theorem tells us that if the product of two elements is equal to E, these elements are inverses of each other. In particular, if A is the inverse of B, then B is the inverse of A. And then, okay, and oh, there's actually this is a misprint. The real version doesn't is with the correct parentheses. Um, so this is actually pretty useful for manipulation. So there's a bunch of things in the exercises that they're kind of they kind of required to do some manipulations. The same kind of manipulations that you do, like solving equations and things like that. And this theorem 3 is very useful for that. So if you have AB and you have the inverse of their product, that is the equal to the inverse of each of the elements in reverse order. And the inverse of the inverse is equal to itself. So the first formula tells us the inverse of a product is a product of the inverses in reverse order. The next formula tells us that A is the inverse of A. So the proof of one goes as follows. So if you have this thing, okay, so how are we going to prove this, right? Essentially, you're going to pick the thing inside parentheses, which is the AB, and allegedly this is its inverse, so you're going to put them on the product here, and if they cumulate to identity, then that's true. So what we're going to do here is essentially some associativity laws. So we're going to do B with B inverse first, and that's going to go identity. Identity with the A inverse is A inverse, and then A times A inverse is E. So this actually holds because of since the product of AB and this is equal to E, it follows by theorem 2 that they are each other's inverses. Then this holds. The proof of 2 is analogous but simpler. So you start with this. So by theorem 2, A is the inverse of a inversed, so it becomes this funny notation here. Um, the associativity law, yeah, this is essentially saying that parentheses are redundant in a very lambda calculus fashion. Having made this observation, sorry, Marinho.
Yeah, parentheses are redundant, and importantly, they are redundant up to every level of nesting. So yeah, you can just omit them completely.
Yeah, having made this observation, you may feel free to use products. Yeah, so we're gonna actually just incidentally by using this identity repeatedly, we find that you can actually like put the inverses of each element in a sequence of products. And then there is a concept of order, which is essentially the number of elements in G. In that set, G being the set, you use the pipes or the bars, I guess. This is not programming. Cool. And then there's another notation improvement for convenience that instead of having to write the A's like a bunch of A's and you have to count them, which is annoying in F, you can just use the exponent for that. The exponent notation, mind you. Okay, so I also have some remarks about these exercises, actually. This one, the first one, I think it's fine. It's just a matter of substitution. Well, that's kind of unfair because technically everything in algebra is a matter of substitution. But this one specifically is a matter of simple substitutions. There's no really an eureka moment in my opinion, because it's just a matter of like doing what this example is showing. So if you have these two, you, um, and you have to solve, and when we say you have to solve, you have to find the value of x. So by the first equation, you can square both sides, and then you do this, multiply on the left by x, you have this, but by the, you can do this becomes this, but this we know what it is about, which is e, and then you can pick multiplying by b squared inverse, then you have this, and you know that this is equal to identity, which means that these must disappear, right? Well, no. Uh, where no, it must disappear because it would also be multiplied on the other side by this, which means that this must disappear, which means that this must be identity, which means that x must be this. So it pisses me off a little bit because usually algebra requires you to have some sort of creativity. For example, oh, let's just do this for the sake of it and see what happens. And usually I suck at that. Uh, People say it is something that can be improved by practice, but I don't know if I believe them. Okay, the next one. For each of the following rules, either prove it is true in every group G, or give a counterexample showing that it is false in string groups. So the first one, is it true or is there a counterexample?
Well, we saw a counterexample already in the XOR case.
The XOR case. Yes, that is true. Next one. If x squared equals a squared and x equals a, is this true?
Is this true? Uh,
You see, that's the problem. This is the problem, man. Like,
well, intuitively, I want to say yes, but
that's
you
not how
know,
that works. That's not how that works. This one is true, obviously, right?
not really, because
Ah,
for
no,
it
no,
to
no,
be
sorry,
true,
sorry. This is only true for abelian groups again.
yeah.
This is not true in general. Uh, this one I kind of don't know because I'm not being able to find any counterexamples. And also manipulating this doesn't give me much. For this one, x squared equals x, then x must be identity. Um, I also want to say yes, but I don't know if I should. For every x in G, there is some x. Well, for every x in G, there is some y in G, such that x is equal to the square. This is the same as saying that every element of G has a square root. I think this is also true, right? I believe.
Every element has a square root.
In G, right?
Well, yes, because if you apply the operation to any pair of elements, well,
You're
by
gonna get.
definition, you're
Yeah,
gonna get something in the group, right?
exactly. By definition, you are still there, so I don't know. This doesn't sound impressive to me.
Like in the worst case, you can pick y equals x, and that is true.
In the worst case, you can say that y equals x. Yeah, but that kind of wait.
Oh, actually, no, that doesn't. I'm thinking of something else.
Yeah, this is what you said is kind of this related to this.
For 2, there is a trivial counterexample on the table that the exercise mentions that both y squared and a squared equals y, but they're different.
Wait, what? Page 28, right? So
29, there's, well, 28, 29. Yes, there is a trivial counterexample there.
okay, so x is square. You said x is square.
Now, there
Yeah,
are
it's way
many
up.
elements of the set that squared equals y equals I, so that's
You mean this table?
yes.
X square equals a square. Then
So
ax
like
is equal to a.
I squared is equals I, but a squared is also equals I, and they are clearly different, so 2 does not hold for that.
What are we trying
Oh well,
to prove there? X squared equals a square implies
yeah,
x equals to a, right?
yeah,
Yes.
which is not the case. Yeah, that is well spotted, Tevo.
Yeah, because in this case, x squared, x being a, and I squared, they have the same square outcome, but they are not the same
But
thing.
they are not equal.
Yeah,
Yeah.
that is true. Thank you, Tiv. Yeah, this is what I said. Why I said in the beginning that I think we're gonna suffer from like some of the exercises. I think we should actually gonna have to use paper to have a like productive discussion about because they are
For
not
every x
like that.
belonging to G, there is some y's belonging to G as well, such that x equals y squared. For every x, I don't think so actually.
Ah, okay. This is actually saying the opposite of what I was thinking. This is saying that you can always find x given some y's that when apply the operation to like two of them, you can go get to x. Yeah, that's pretty bold, actually.
For every x, there is some y such that this holds. That is the same as
For
saying that
that,
every element of G has a square root.
Div,
for that
Oh,
to
that
be
is clear. Well, for that to be true, square root of 2 would have to be a rational number in the group of rational numbers.
no, but that G is not rationals necessarily. Go Div.
But that's a counterexample, no?
What do you
oh,
mean?
and I was just going to say that another counterexample is that that would mean that if you draw out the table of operations, then it would mean that the diagonal of the table would need to contain all of the elements of the set, and that is clearly not true for the table we have on page 28.
Wait, what you said is that the primary diagonal, right, should have all the elements contained in the set.
Yes, because it means that every element could
That
be the
is
square
true.
of another element.
That is true, Marinho. Do you follow?
I do follow, yes.
Yeah, that is true. So let's put this on the screen. Yeah. So in this example, okay. So why is that? It's because for the primary diagonal is always going to be in this case the multiplications of the the y in this case. So all the possible y's. So a square, b square, c square, d square, and k square, and identity square. And saying that for every x containing g, x being all of these six, if you must have x equals to y squared, this means that all in the primary diagonal, all of the elements in the set should be contained in the diagonal, which is not true, as you can clearly see here. So that's again very well spotted too. Uh, okay, so where are we? We're here. Okay, so for any two elements x and y in G, there is an element z in G such that y is equal to xz. This means that, yeah, well, I don't know if this is true for every group, but I think this is true for the table, right, Tiv? I think it even says in the text that this is true.
Uh, for any two elements, um, of
Where is the table? Yeah, here it is.
there we go. For any two elements, there must be
And
a
another
third
third
element
element that you can
that you
multiply.
multiply by one to get the other.
Exactly. Yeah, this is clearly true for this table, right?
Hmm.
For every combination of elements, you can get another one by multiplying by
Yeah, it is true
something.
because there are no repeated elements on any rows or columns.
Yes, and there's an exercise we will see later. We
Yeah.
cannot have any repeated elements in
Yeah,
any
yeah,
rows.
there are consequences of having repeated elements in the same row.
Which
But
means if
that is
there are
not enough
consequences,
though. Sorry, David.
what are the consequences exactly?
That's what we're gonna prove. That if you do have that, what does this mean? That's what the exercise
The
is asking you for to
consequence,
do.
the consequence is that those two elements
Are the
which
same.
appear, which are the same, they actually collapse into being the identity element.
Wait, I didn't reach the identity conclusion. I only concluded that if you have in the same row two elements that are the same, that must mean that the columns are the same.
Oh,
What?
which means that property 6 is true for every group, because if it wouldn't be true, then you would have repeating elements on a row.
Wait, repeat that.
It means that property 6 is true, because if it weren't true, you would have repeating elements on a row, and that would cause problems.
Ah, that is true. I guess that is true. Yeah. So 6 is right. But I am still we're gonna go to that exercise, but I'm interested to see what Marinho said about the collapse into identity. I haven't reached that conclusion myself.
Collapse into identity. Actually, I think I might be misremembering. I did this earlier today, and I didn't write anything down because I'm
That's
silly.
I think we should not. I think we should stop doing that. I think we should all buy tablets on like AliExpress and connect our computers and draw that stuff. Really.
I bought a good old-fashioned notebook and pencil, and then doing the exercises with that.
No, but that's a problem because to share that, you're either gonna have to take a photo and send that to like a caveman, or you're gonna have to use your camera and point at a notebook.
But that's fair.
So that's why I'm talking about the tablet. Oh, not tablet, the drawing surface, right? Elements that commute. So if A and B are in G and they commute, we say that they commute. Assuming that A and B commute, prove the following. So A and B commute, right? So this is provable by the inverse thing. So the theorem of the because what you're gonna do, you're gonna say that A inverse times B inverse equals B inverse times A inverse. So, but you're gonna have to do some rearrangements, right? That's essentially the trick here. But which arrangement are you gonna do?
Actually, you can do this by just multiplying on the same side by both of the inverses. Well, like if you do AB and then A inverse and B inverse,
Theorem 3.
um, yeah, you have to prove that that is equal to AB, B inverse, and A inverse. And that's fairly easy to do if you just use the commutativity of A and B.
Um, sure. Kind of hard to picture, but sure. Um, A commutes with AB. A square commutes with B squares. Actually, this is every like exponent operation in this case is already like trivial to prove that because that this can be recoded as in terms of A's and B's, and because you know A's and B's commute, then you can just rearrange them, and then you go back to the exponent notation, and you're good to go. Then, and again, this is the type of exercise that I hate because this needs creativity, right? You need to know what you're going to multiply on both sides. Sometimes it can be trivial, but some other times that's not going to be the case. So what you were suggesting here, Marin, first to multiply on both sides?
Like start with AB, and then
Theorem
you have
3.
to basically yeah, you have to basically prove that AB A inverse B inverse is equal to AB B inverse A inverse, essentially.
Okay. Group elements and their inverses. So then this talks about prove that if A, B equals to E, then B, A equals to E. Uh, this is Well, it's not an abelian group, so you cannot just flip that, right?
Oh, but they are inverses of each other.
Yeah, they are inverses of each other. But what does that? Oh, you can use that fact here and say that B is actually with B inverse, which is, and this is tautological, so that holds. So again, more manipulation of things, not necessarily interesting. This one is actually pretty interesting, actually, because it's an unexpected connection about it being odd or being even, and the fact that elements are their own inverses, right? That's kind of cool.
Right.
So imagine that you have G as a finite group, and it has to be the set of all the elements of G which are not equal to their own inverse. So S can be denoted in this way. The set S can be divided up into pairs so that each element is paired off with its own inverse. So this is essentially what's going to happen. Like you are grouping them together by C and its inverse. And why do you know this is possible? Because by the definition of group, every element has an inverse contained in that group, and because S is only the ones that are not themselves, there is always like a pair. In any finite group, the number of elements not equal to their inverse is an even number. So why is that true?
Well, because for every element which is not equal to their inverse, you have the
There
inverse,
must be a
which is
pair.
different from it.
Yeah,
So, yeah.
yeah, that's cool. The number of elements of G equal to their own inverse is odd or even, depending on whether the number of elements in G is odd or even. That is also pretty cool. Why? Because you always have to count that there is the neutral element inside there. And that's actually pretty important for, I think, both of these two here.
Uh, well, for the two, that doesn't matter too much. It's basically saying, okay, we know from one that if an element is different from its inverse, then the size of that is even, right? But an even plus an odd is odd, and an even plus an even is even. So having that extra number, extra even number of elements doesn't affect the evenness or oddness of the entire group. So
No, but it's
yeah,
the opposite. We want to conclude we want to make a relation on the opposite direction, Marinho. We know the odd or evenness of the G. We are try to understand the evenness or the oddness of this one. So let's suppose that G is
uh,
odd, right? The order of G is odd.
that means that the number of elements of G which is equal to its own inverse is odd.
Uh, is that true?
Well, yes, because like
Yes,
the
it must
number
be
of
true.
elements of
No, it must
G
be true.
will I yeah, because the G will either have an odd number of elements or an even number of elements, right?
Yeah, if it's odd
But
and you remove identity, then you have even elements.
no. You don't remove identity actually because identity is equal to its own inverse.
No. But in this case, I'm paying attention to the ones that are not, because then I can do the subtraction in my head to get this one,
You
over. But what you're saying also
yeah,
works. What you're saying also works. So what you're doing is you have an odd number of elements in G. The order of G is odd. Then it must be odd the ones on the inverse, because
because the ones that are not equal to their own inverse are always going to be even, and an even
exactly,
number plus an odd number is odd.
exactly. But if G is even,
Same
then
argument.
then then it's still odd. That's what you're saying.
No, it's the same argument. If the number of elements of G is even, then the number of elements that are their own inverses is also even, because the number of elements that is not their own inverse is necessarily even, and even plus even is even.
Yes, yes, that is the case. If the order of G is even, right? So there is at least one element E in G such that it's not the identity element. and it is equal to its own inverse. And that must be true, right? Because if G is even, you have all of a bunch of pairs of the ones that are not equal and the identity. So but everything in totality must be even. So you must have another one by necessity, right? So
Yes.
to make the other pair with
Yes.
identity. Um,
That does follow.
yeah. So why is this true? Because, well, assuming that it is an abelian group, G in this case is not only a group, it's an abelian one. This is true because when you put like when you substitute this with another a1 all the way to an, and you keep rearranging them, right? You're eventually gonna pair up all the inverses with each other, and then it's gonna be equal to identity all the way.
Yeah.
If there is no element x equals to different in identity, then everything is equal to identity in the operation, of course. Well, no element different than identity such that x is equal to itself. So you're saying there are no elements in G
I,
that are their own
yeah.
inverses,
Yeah.
aside from um, neutral element. Then if you apply the operation on all the elements of G, then it must be equal to E, and that is the case precisely because it is an abelian group, which means that you're going to be able to rearrange this. It's a similar argument to 4. If there
Yeah.
is
Same thing for 6 actually.
if there is exactly one element, then you're going to do the same, but you're going to have a lonely guy there. And that lonely guy is that.
It's the owner of a lonely heart.
Constructing small groups. Yeah, so yeah, this is the one about the row with the two things. So in each of the following, G is a group. We have a neutral element, of course. If A and B are any elements of G, prove the following. So if A square equals A, then A must be equal to E. Is that true?
I have just a comment on the previous exercise. There is
Yeah.
also a geometrical representation for the second one, which is that for an even number of elements, every element that is the opposite of the zero element on the circle is also going to be its own inverse. And if you have an odd number of elements, there's
Wait,
no
could you
element
could you
on the
repeat
opposite
that?
side.
Man, having no pictures for this is hard. Could you repeat that? I'm very dumb.
Okay, if you lay the elements down in a circle like we
Yes.
were doing before,
Yes.
every element that is the opposite side of the zero element is also going to be its own inverse.
Yes.
And if it's an odd numbered set, then there will be no element that is exactly the opposite side there, because you can divide the set neatly in half.
That works for modular arithmetic, but does that work in general?
Uh, that is a good question, actually.
I was not thinking of the circle in modulo terms this time, Marinho. When Tevo said imagine a circle, I imagined, and I was using as criteria to make the circle each line connecting 2 points going through the middle, they are inverses of each other.
That is not necessarily true.
No, of
Um,
course it is not necessarily true. But that's what I was thinking when you said what you said. Because in this case, this holds for identity, right?
uh,
Yeah, no, neutral element. Sorry.
wait, what holds for neutral element? Sorry.
The neutral element's inverse is itself.
No, sorry,
Oh, but
about the line specifically.
No, no, no. Yeah, the line I was trying to make in my head was if you have a line, you are your own inverse.
If you have a line going straight to the center, that's intuitively that makes sense
Yeah, I
to
don't know if
me.
it holds in general.
I don't know how to prove that.
well, for modular arithmetic, every line goes through the center,
Yes. Yeah.
but only potentially two, one or two elements can be their own inverses in that case.
But no, not every line goes to the center.
Mm, I think Marinho is talking about in modular arithmetic, finding inverses always goes through the center.
Not necessarily, no. If you have like a
Really?
circle with, if you have a set of 6 elements, then the inverse of 5 is 1, for instance. And if you draw a line that on a circle, that won't go to the center.
The inverse of 5 is 1. Oh, right, so that is actually true.
Ah, yeah,
Never
that is
mind.
true. That is
The
You would
true.
only
have to
ones that
rearrange.
are going to. No, sorry.
Anyway, but that's cool that you imagine the circle there. That's cool.
The only line that is going to go to the center is the line between the two inverses, if you have two elements that are their own inverses in this case.
Uh-huh. Oh yeah, so you proved via counterexample that in the case of modulo, the circle idea that I proposed doesn't apply for every group. Sure. Uh, if a square equals a, then a equals e. Is that true?
Yes, it is.
Yeah. If ab equals a, b must. All of these are using the theorem about the neutral element, right? All of these.
Yeah, those are all based on cancellation.
Um, Cancellation. Yeah, sure. That is the case. Explain why every row of a group table must contain each element of the group exactly once. Uh,
Yeah, no, now that I have the table in front of me again, yeah, it's not about collapsing to identity. They are equal. Like
yeah,
y1
y1
and
and
y2 will
y2
be
must
equal
be equal, right?
because of cancellation again.
Um, because of cancellation. Yes.
Yeah, because we're
Yes.
basically
No. Yeah.
saying,
Yeah. You basically say a y1 equals x, a y2 equals x. You bring those two equalities, you put them together, and then you cut the a, so you have y1 equals y2.
yeah,
Which means that they should not be separate columns. They should be a single column. There is exactly one group on any set of three distinct elements. Yeah, this one I'm a little bit sus about because it's saying to keep in mind parts one and two, and what I think it means is that these three things combined means that you cannot arbitrarily put B or E in these two positions here. There is
yep.
only one thing that fits that these two things hold. For example, a squared equals a, then a must be equal to E, because it's essentially saying that this a and this a they must be like how should I say this? Well, it's also saying
They
that
must
AB is equal to A. So if AB is equal to A,
then
um,
b equals z, which
yeah,
is not really a third distinct element.
no, no, but let's backtrack a little bit. So what are you gonna put on the AA case?
B,
I'm gonna put B on the AA case. Why?
because this is isomorphic to addition modulo 3, and 1 plus 1 equals 2.
Well, I don't think that's what the exercise was trying to go for. I think it's trying to make us understand that when these three things mean something if there's only three things. But I guess you can do the isomorphism that you proposed. So you were saying that AA is going to be equal to B and AB is going to be equal to E.
Like, this is not at all what the exercise intends, but if you relabel E to 0, A to 1, and B to 2, it's very obvious what you have to do
Yeah,
here.
but that's cheating, man. That is definitely cheating. So if AB is equal to B, and yeah,
Well, A squared cannot be E, because then,
then
because then that would mean that we would need to have an even number of elements, but we have an odd number, as per the previous theorems, right? Uh, and it cannot be A because of the cancellation we saw above, where A squared equals A implies that A
no,
is
no, no.
E.
My
So
question in
the
the
only
A,
option is B. Yeah.
I don't, I just don't get the first one, the first argument. It cannot be um, A because of this other A here, which means it can be either E or B. What is it gonna be? And why?
It has to be B because if it's E, then you're basically saying A squared equals E,
Yes, which means
which implies that A times B must be B, which implies that A is equal to E.
wait. You said that A B
Like if you
paper
put
lack
an
of
E
paper.
on like if you put an E on the A squared, the only option you have left for B is B.
B. I agree on that.
So you're in the case where A B equals B, which means A equals E, which means this doesn't actually have three elements.
Ah, I see. And the same thing applies for B. Then you can do kind of the same with four elements with the extra requirement that x equals e. So like x squared equals e, which kind of means that the entire primary diagonal is a bunch of e's. And then you probably do the same thing that you just did on the previous exercise to fulfilling the holes, and you're done. And then 5, same thing, but then again there's extra requirements. I think it's going to be pretty similar. And then use exercise E3 to explain. So E3, this one, to explain uh, why the groups in parts 4 and 5 are the only possible groups of 4 elements, except for naming the elements with different symbols. I don't know how to. I don't know about that one. I would have to. I really need paper for this one, right? What you would you do? Do you have comments about this one, last one, Marie?
Uh, exercise E3, that's about the parity argument, right?
Yeah, it's talking about if G is even, then there's at least one element X in G such that these two things are true.
Uh, right, because yeah, at least one of the yeah, I think this has to do with like what you cannot do when you assign the values of the results, because we did the exercise where the diagonal is all e's, so everything is its own inverse, right?
Yeah.
And the other case is, okay, what if there's only one where that's its own inverse and it's different from E? Then that means, then necessarily, because you only have two elements left and they cannot be their own inverses, they must be each other's inverse.
Yes.
And that basically fixes the rest of the table.
Yeah. I don't know if I followed 100%, but I think I followed the most of it. What you said. Again, we really need to buy the tablets. Well, I only have to connect the tablets. I can give you a tablet, money. Because man, this is so freaking hard without having like concrete evidence, as probably Tevo has in front of him. Then we talk about direct products, blah blah blah. Again, this is essentially what Cartesian products, and we have to
Yes,
prove
and
they are groups. Go on.
yes, and the operation is extended in the same way that you would make a dot product, basically.
Yeah. And then there's a bunch of intuitive things, like if G and H are abelian groups, prove that their Cartesian product is also one. And then finally, we have the powers and roots of group elements, which again probably require a bunch of manipulation and eureka moments to say things. And then the thing that matters is that there is an element x in G such that a is equal to a squared. We say that a has a square root in G. And the same thing for a cube root. And then if you say that a 3 times is equal to e, then a has a square root. How do you prove this one?
How do you prove this one? Well, in order to get to E, you must multiply something by its inverse, right?
Yeah.
So let's assume that A is the inverse to something else, which would be A squared in this case, right?
Yeah.
Um, well, clearly A is not its own inverse because A times A squared equals E. So there must be something that is equal to A squared that's not A.
Wait, repeat that. Because I got your
Like,
point that A is equal to the inverse of A square. I got that.
well, yes, A is equal to the inverse of A squared,
Yeah.
right?
Yes. Good so far.
Um, but that means if A is the inverse of A squared, there must be something else which is equal to A squared, which is not A,
Uh,
which
that thing has to be the inverse of A, in fact. If you
well,
represent the A to the third power as A squared times A, and then you multiply by the inverse of A, then you get A squared equals A to the inverse.
Wait, repeat that, Theo. Man.
Uh, Instead of writing A cubed equals E, you write A squared times A equals E, and then you multiply both sides by the inverse of A, and then you get A squared equals inverse of A
Oh yeah,
by
that's
like
doing the
trivially.
opposite. That's doing the symmetric move, Marin, that you just did. Tevo did the other way, and he reached that A square must be equal to the inverse of A,
yes.
which is the symmetrical result that of what you said, which is A must be equal to the
And
inverse of A square.
yeah, and critically, A is not equal to A squared. A is not its own inverse because then A squared would be E. So that would lead to a contradiction.
But we haven't reached the square root part though.
Why would that be a
Uh,
contradiction?
because if A cubed equals E, well, actually, I guess technically that can be true if A equals E.
Yeah, that's kind of just a special case, but
Yeah.
it is
Uh,
technically valid.
well, again, I think for these exercises to be more productive, we should have like the elaborations that we um, because I'm still a little bit confused about. I followed everything that you guys said about this, but I still haven't concluded that A has a square root. So maybe well, it is definitely a skill issue. Okay, so next chapters for next time. So are we doing 5 and 6? How many pages is that? I should not have done what I just did. Yeah, see this. So one, two, three, four.
Subgroups.
Yeah, and then how many exercises? A bajillion
There's a lot.
exercises. Okay, and what about 6 functions? One, two, three, 4, 5. And how many exercises on functions? Holy jeez,
A lot.
automata. Okay, so Tev, what do you think? We only do chapter 5 or do 5 and 6 next time?
I think if we do 5 and 6, we're going to way overshoot the time.
So only chapter 5.
Yeah, I do think only chapter 5 is probably fine.
Okay, I'm gonna finish the recording.